This is AP Calculus 4-7, and we're going to talk about L'Hopital's rule. L'Hopital's rule will save you a lot of time. It only works when you have the indeterminate form, and more specifically, you need to have the indeterminate form 0 over 0 or infinity over infinity. So I want to look at an old example of a limit, and we use this to solve limits of an indeterminate form. We can use derivatives to solve these limits. So I'm going to look at an old example and how we did it before, and then I'm going to show you how L'Hopital's rule works. And you're going to see that using L'Hopital's rule is just going to make everything so much simpler. So with this one, if we plug 1 in, we would end up with, let's see, 1 plus 4 is 5, minus 5 is 0, and then 1 minus 1 is 0. So we end up with the indeterminate form 0 over 0. So we know we can't just plug into this to find the limit. So before, when we did this, the first thing we did is we simplified using algebra. So x squared minus 1 is x plus 1 times x minus 1. That's the difference of squares. And then factors of 5 that subtract to give you 4 would be 5 and 1. And the signs would be a plus 5 and a minus 1. And then we figured out that we could cancel those two out, leaving us with the limit as x approaches 1 of x plus 5 over x plus 1. And now if I plug 1 in and just do direct substitution, I have 6 over 2, which gives me a limit of 3. And that's fine. That's not terribly difficult. And anytime you can use factoring to solve a limit, it's not really a difficult problem, but there are some problems that we did some factoring or we multiplied by the conjugate and things like that, that L'Hopital's rule, it's going to save you a huge amount of time. So I'm going to look at this using L'Hopital's rule now, and anytime you have an indeterminate form, 0 over 0 or infinity over infinity, L'Hopital's rule can be used. L'Hopital's rule says that I can take the derivative of the top and the derivative of the bottom and then do direct substitution. So that's what I'm going to do. So this is the limit as x approaches 1, and I'm going to take the derivative of the top, which would be 2x plus 4, over the derivative of the bottom, which is 2x. And now I'm going to plug a 1 in doing direct substitution. So if I plug 1 in, I get 2 plus 4 is 6 over 2, which gives me 3. That is, in fact, the limit. And every time we use L'Hopital's rule, we're going to get the same limit that we got when we did all of the algebra. And keep in mind, when we did those conjugate problems where we had to multiply by the conjugate, where we had maybe like the square root of x plus 1 minus 5 over something, and we had to multiply by the square root of x plus 1 plus 5, the conjugate of that top, the algebra in that got pretty difficult. So using L'Hopital's rule is going to kind of save us a lot of time. So here is L'Hopital's rule written out. It basically says, L'Hopital's rule, if the limit as x approaches c of f of x over g of x, so we've got the limit of a function over a function, produces the indeterminate form 0 over 0 or infinity over infinity, and if the limit as x approaches c of f prime of x over g prime of x equals L, then the limit as x approaches c of f of x over g of x is also equal to L. And the good news about L'Hopital's rule is this. If you do L'Hopital's rule once and you still get the indeterminate form, all you have to do is continue to do L'Hopital's rule over and over again until you get something that works. And that's what's nice about this, because sometimes doing L'Hopital's rule once doesn't work, but when you continue with L'Hopital's rule, take the second derivative and the third derivative, then you get the answer very easily. And if you think about the type of functions that might happen with, the algebra can get pretty difficult in those type of functions. That's why L'Hopital's rule is a method to save us a lot of time. So I've got two examples here that we're going to try using L'Hopital's rule. And make sure before you use L'Hopital's rule that it is the indeterminate form, because you don't want to assume that you need to use L'Hopital's rule every time you have a limit. That's not necessary. So we're going to always make sure we plug in first, do direct substitution to make sure we're getting the indeterminate form before we do L'Hopital's rule. So if I plug 2 in, I get 4 plus 2 is 6 minus 6 is 0. And then 4 minus 4 is also 0. So we do have the indeterminate form 0 over 0. So I'm going to have to use L'Hopital's rule. So I'm going to take the derivative of the top and the bottom. So the limit as x approaches 2, the derivative of the top is 2x plus 1 over the derivative of the bottom, 2x. I'm going to again do direct substitution. So 2 times 2 is 4 plus 1 is 5. And 2 times 2 is 4. So the limit there would be 5/4. The limit as x approaches infinity of e to the x over x squared. Now if you think about this, if x is infinity, well, we have e to infinity. E, remember, is a constant. So any constant other than 1 to infinity is going to make that approach infinity. So we've got infinity. Infinity squared is also going to be infinity. So this is the other L'Hopital's rule situation where we have infinity over infinity. I'm going to take the derivative of the top and the bottom. Derivative of e to the x is e to the x. The derivative of x squared is 2x. Now I'm going to do direct substitution again. E to the x gives me infinity. 2 times infinity is again infinity. So I'm going to use L'Hopital's rule a second time because by the definition, I'm allowed to do that. Now I just take the derivative of our new function that we have. So the limit as x approaches infinity, again, the derivative of e to the x is e to the x. The derivative of 2x is 2. Now I have infinity over 2, which gives me a limit of infinity. So our answer here is infinity. We use L'Hopital's rule twice. So now, anytime I get the indeterminate form 0 over 0 or infinity over infinity, I'm going to automatically jump to L'Hopital's rule because it's going to make life a lot easier. And this is just a method that we couldn't learn until we knew how to do derivatives. Here are 2 more examples. If I plug infinity in, I have infinity plus cosine of infinity. Well, infinity plus anything is going to be infinity. And then that's over infinity. So that is the situation, infinity over infinity. So we're going to try to use L'Hopital's rule to see if we can get this one to work out. So if I take the derivative of the top and the bottom, the limit as x approaches infinity, the derivative of x is 1. The derivative of cosine x is negative sine x. And that would be over 1. Now, if I separate that out, I know that the limit as x approaches infinity of 1 over 1 is just 1, minus the limit as x approaches infinity of sine x. Well, if we think about that, if we plug infinity in, isn't sine going to be an oscillating function? It's going back and forth between 1 and negative 1, and that pattern is going to continue forever. So here, L'Hopital's rule is not going to work for us, so we need to find another way to do this problem. So I'm going to try to rewrite this. That is the same thing as the limit as x approaches infinity of x over x plus the limit as x approaches infinity of cosine x over x. I'm allowed to do that because the limit of the sum is the same thing as the sum of their limits. We learned that back when we were doing properties of limits. So here, if I just simplify this, that's the limit as x approaches infinity of 1, which is just 1. So we know the limit here is just 1. For this one, the limit as x approaches infinity of cosine x over infinity. Well, if you think about cosine of x, the only answers for cosine of x, no matter how big my infinity or my number that I'm plugging in for x gets, isn't that going to fluctuate between 1 and negative 1 all the time? If you think about what the trig function of cosine looks like, it's that trig curve, right? So it's fluctuating between 1 and negative 1. Well, if we put all the numbers between 1 and negative 1 over infinity, isn't that thing going to approach 0? So if that section approaches 0, or that part approaches 0, then 1 plus 0 is just 1. So we were able to find the limit of that one without using L'Hopital's rule. In the next one, this is one of those that when we did that before, if we plug 4 in, we get 0 over 0. So it is the indeterminate form. And before, when we did this, we would multiply by the conjugate here. Instead of doing that, I'm going to use L'Hopital's rule. I'm going to take the derivative of the top over the derivative of the bottom. So if I do that, the limit as x approaches 4, the derivative of the top is just 1. The derivative of the square root of x, that's x to the 1/2. So that would be 1/2 x to the negative 1/2. So the limit as x approaches 4 of 1 over 2 square root of x. Now if I plug 4 in, I end up with 1 over 2 times 2 is 4, which gives me a limit of 4. And I could have multiplied by the conjugate on the top and the bottom, but you see that algebra would be a lot more difficult than taking the derivative. Go ahead and pause the video, see if you can get these on your own, and then we'll come back and talk about them. So looking at the first one, if I plug 0 in, I would have 0 over sine of 0 is 0. So I would have 0 over 0. That is the indeterminate form. So I'm going to try to take the derivative to solve this one. So it would be the limit as x approaches 0. The derivative of the top, I'm going to have to use the product rule. So the derivative of the first thing would be 1 times the original second plus the original first times the derivative of the second would be secant squared x. Derivative of tangent is secant squared. And then the derivative of the bottom would be, derivative of sine is cosine, so we've got cosine 3x times the derivative of the angle part, which is 3. Now, don't get confused and think you have to use the quotient rule here. Remember, taking the derivative using L'Hopital's rule, we take the derivative of the top over the derivative of the bottom. You're not doing the quotient rule. The derivative of the top would be the product rule over the derivative of just the bottom. So don't get confused about that. I could see where that might be a common mistake that students would do. But remember, L'Hopital's rule is derivative of top over derivative of bottom, and then you do the direct substitution. So now if we plug 0 in, and I'm going to draw a little unit circle here so we can talk about the math here. When I plug 0 into tangent, this ordered pair is 1, 0. So tangent of 0 would be sine over cosine. 0 over 1 would be 0. Plus, when I plug 0 in here, well, we've got 0 times secant of 0. So it doesn't matter what this is. 0 times anything is going to be 0. So we have 0 on top. And then on the bottom, we have 3. Cosine at 0 is 1. So we got 3 times 1. Well, 0 plus 0 is 0 over 3 gives us a limit of 0. This one is a little bit more difficult because if we take the derivative, we're going to be using the chain rule. And we've also got natural logs and some an e function. To make sure we can use L'Hopital's rule, remember the first thing we have to do is plug infinity in. So natural log of infinity is going to be infinity, and infinity squared is infinity. And then e to the 2 times infinity, well, e, remember, is a number, 2.7 something. It keeps going. And then e to, or that 2.7 something to the infinity power would be, again, infinity. So we do have the indeterminate form infinity over infinity, so L'Hopital's rule should work. So if I do this one, we've got limit as x approaches infinity. If I take the derivative of the top, I do have to use the chain rule. So to use the chain rule, I take 2 times the original function, natural log of x, decrease the power by 1, so that'll be a 1, and then I take the derivative of the inside. Well, the derivative of natural log of x would be 1 over x. So this would be times 1 over x. So that whole thing is just going to be over x when I simplify it. And then the derivative of the bottom, remember the derivative of an e, I take that and I write it again. And then I take the derivative of this part, the exponent part, so that would be 2. So there's my derivative. If I want to rewrite that, I would have the limit as x approaches infinity of 2 times the natural log of x over 2x e to the 2x. And I could cancel out the 2's. Now, if I plug infinity in, I get infinity over infinity again. So that is still the indeterminate form. So I'm going to try L'Hopital's rule again to see if I can get it to work. So the limit as x approaches infinity, the derivative of natural log of x is 1 over x. The derivative here, I'm going to have to use the product rule. So what I have on the bottom is x e to the 2x. So the derivative of the first thing is 1 times the original second thing plus the original first times the derivative of the second, which would be e to the 2x times 2. And now if I plug infinity in, on the top I would get 0. On the bottom, I get infinity plus infinity, which is infinity, which will leave me with a limit of 0. So L'Hopital's rule works there. I just had to use it twice.